we're going to take a look at some important amines that you'll find in biology and chemistry. The first are biomolecules, so amino acids, of course, contain amines, as do proteins, which are built from amino acids. Then DNA and RNA those contain the bases connected like adenine, guanine, cytosine. And if we get a chance later in the semester, we will look a little bit at the structure of DNA and RNA. As we've already talked about, many pharmaceuticals just one example, really common high cholesterol medication, Lipitor. If you look up its structure, you'll find that it has a pyrrole core. And then alkaloids. Alkaloids are heterocyclic amines but they're isolated from plants. So alkaloids are natural products, whereas Lipitor is a heterocyclic amine. It's not a natural product, it's synthetic. So just some examples of common alkaloids. One of my favorites, caffeine, then morphine, nicotine, and even things like cocaine. Morphine is sort of an interesting example that we'll take a look at. So the structure of morphine contains several fused rings. The nitrogen is a tertiary amine. That's in this bridged bicyclic. So here's morphine. And morphine is isolated from the opium poppy. Now, while this is a natural product, it's frequently used in medicine, and the amounts needed for medicinal purposes can't be all isolated naturally, so there are also synthetic routes to make morphine synthetically. Now, if we look at this, we have 1, 2, 3, 4 groups that can hydrogen bond with water. For 17 carbons in the molecule, which comes out to about 1 for every 4.25 carbons. This is right on the cusp of the rule of 4, the rule of 5, and morphine is in fact water soluble. So there's enough hydrogen bonding capable groups for the number of carbons to overcome the greasiness of the carbons to make it water soluble. So now what can be done with this is it can be reacted with something like acetic anhydride, and actually 2 molecules of acetic anhydride. And what this will do is an acylation reaction and put acyl groups on these oxygens. To get this molecule. Now we have these acyl groups on the oxygens. And this is actually the structure of heroin. So this is one of the synthetic routes that people who are illegally trying to synthesize heroin will take, is by reacting morphine with acetic anhydride. But the byproduct of this reaction comes from the other half of acetic anhydride. We get 2 molecules of acetic acid. And acetic acid is just vinegar, and I think everybody knows the smell of vinegar. Well, when there's trace amounts of, or there's always going to be trace amounts of acetic acid in this heroin, and this is actually what drug dogs can smell and detect. Even if there's very small traces in it, dogs have a more keen sense of smell than humans and can sniff that out. Also, even certain criminals that think they're going to be clever, and instead of using acetic anhydride, they think, well, let's use an acid chloride to put the acyl group on it, and the byproduct is HCl instead of acetic acid. The problem is these acetate groups, in the presence of moisture from the air, some of them are going to get hydrolyzed to acetic acid anyway, so regardless, there's going to be acetic acid in the sample that can get sniffed out. So, comparing heroin to morphine, it's less polar. Because we've added on the extra carbons, making it more greasy, which means it's kind of now right on the cusp of being both fat and water soluble. Which that kind of hits the sweet spot for potency, being right there on the fat, water soluble border. So heroin is much more potent than morphine.